back into paper 1, which is book 1, which is paper 1 for the June and prelim and end exam. We are busy doing calculus now. Now, calculus is something that you use especially in engineering. And calculus, the very practical application of it is for gradients. Now guys, the reason why I want to just put you in the picture because I'm going to say, okay, let's do limits, and you think, okay, limits. And then we're going to start doing the actual derivatives, and you're going to just do it with me. But I'd like you to, in the back of your mind, focus on what I'm saying to you now. We are going to be busy with gradients. Now gradients, as you know it, is basically more inclined on a straight line. We've got a continuous gradient for the whole straight line. It's always the same. But there's always also gradients like in, for instance, a parabola. If you have a parabola that is a frowny face, then you've got a positive gradient turning into a negative gradient. And is the gradient constant from one point to another? No, because it changes a little bit. Now those gradients we're going to apply for your final graph that you're going to do now. You've done straight line, you've done parabola, hyperbola, exponential in grade 11. This year you also got to the log graph, which is together with the exponential one. And now the sixth one that's coming, not today, not in a few days, it's going to be the cubic graph.
Okay.
And to do the cubic graph, we're going to have to work with gradients, and this is where calculus comes in. So if in the back of your mind, all the time you're thinking, what is calculus? It's working with a gradient. Then you've got something to stand on and hold on to, although you don't know much yet. Okay, now inside of those sums, we are going to get a formula that has got something to do with limits. Now guys, limits is a vast subtopic of mathematics, which you don't do. What I'm teaching you today with 3 sums is basically, I want to say untrue, but it's not what limits really are. Limits are when you're busy with graphs and stuff that you tend from one side to another side to look at what's continuously happening in specific places, which doesn't mean anything to you. I'm just going to teach you, if you see the word limits, do substitution. I'm putting it on this video, but please don't quote me on this, because it's not true mathematically. What you're going to do with it is you're going to do substitution. So if I say, work out the limit, now there's a few rules here. This is in one line in your book, on one line. So it means LIM standing for limit. Underneath it, it says where x tends to be 1. So it's nearing it and not really quite getting there. And then you get the x squared plus 1. So I'm applying a limit to this expression. And actually I like it if you put it in a bracket, although for this particular one it didn't really matter. But what I'm telling you today, very unmathematically, please don't quote me on this, I'm telling you that it's not quite the truth. You're just going to do substitution. So when I told you that now, what's the sum going to look like? 1 squared plus 1. And then you don't put this here anymore because you've done what I asked you to do. And this answer would be? What does that mean? Nothing for you. If in a graph, in a specific place, you had this parabola and that you were tending from left and right into that point there at 1, it would tend to be equal to 2. But even if I say that, it's more confusing than what I didn't say it. If man teaches you about limits, I'm teaching you just substitute. With one or two things that can happen, and that is if in the next example of a limit, I substitute, what's going to happen to this sum? If you substitute x with 2, it's going to be undefined. So there's one thing to look out for. If you substitute and you get undefined, then you should have factorized. That's the only thing that can happen, and they never ask you these questions, but maybe sometime, somewhere, maybe you'll meet up with something like this, just to be safe. So if I give you that and I tell you you should have factorized, how would that have happened? What would I have written?
X minus
x minus 2, x plus 2 at the top, which then means that I can substitute. But have I substituted yet? So x is still tending to be 2. That x there. But now that it's simplified, then I'm saying I'm going to substitute the 2 into x plus 2. Now it's not undefined anymore. It's going to be 2 plus 2, which is 4. Have you got a good idea what limits are now?
Yes.
No. Please don't think that you do. I'm just teaching you. If you need it somewhere, just know that limits you're going to do for your purposes with substitution. If something is undefined, you should have factorized. Are there undefined limits? Yes, there are. It's not on our syllabus. It's not on our level. Okay, next one. If I then ask you for that last question to ask if you really know about limits, you still don't. What must I do?
Substitute.
Substitute your k with
0.
in everywhere. So what's this answer going to be?
0.
Because 0 squares, 0 times 3 is 0, 0 times 6 is 0, and add them together is still 0. Please don't quote me on this. Limits are substitution. Right. Right, so what's going to happen in a sum when you have to do calculus or differentiation or find the derivative? I haven't written this there. Finding the derivative. It's just all derivative. No, I spelled it wrong. Okay. Finding the derivative. All of them are synonyms for doing what we're going to be doing now. So first of all, when I ask you, I'm going to get back to this just now. When I ask you to find the derivative, there's lots and lots of things that I've got to specify. Now sometimes we're a little bit like, oh, you can do basically whatever you like, but in calculus, they are very, very concerned about your notation, your way of writing it. And then there's 4 notations. Now, if I give it to you in function notation, written as a function, then you've got to write your derivative like this. You're going to have f with a little accent. Not to be confused with, what's that? Inverse. So guys, read. Sometimes they ask this in a question and you all of a sudden think it's inverse, but it's actually derivative or the other way around. Are you with me? Know what you're doing. So the notation is very important, that if I give it to you in function notation, you write f is the function, this is the derivative. Now let's go back and see what I've written over here. Now let me do this first. The rule in plain English is take your separate terms, coming back to this now, they have to be separated terms. So if there was 2 brackets timed with each other, you couldn't do this, what I'm going to show you now. They've got to be separate terms. How many terms are there? 4 of them, right? If they are separate, that's fine. There's also another rule that says there mustn't be a variable in the denominator. That's going to be this next one. Okay, so that one's fine. Also, you shouldn't have roots. Roots must be written in exponent form, coming. So this one's okay. It's separate terms, there's nothing that shouldn't be there, and I can do derivative. Now this whole process of derivative is in plain English. You take term by term, you take the exponent times the coefficient, so 3 times 3 is? No, not 6. X to the. Then you take one whole integer number away from 3. So you subtract 1. And it gives you 2. What is going on here? So now please remember in the back of your mind that differentiation is going to get you to the gradient. We are working towards a goal. It's going to get you to a gradient. But now let's complete the sum, because this is going to happen again and again and again and again. Next term, what do? Exponent times coefficient gives me minus 4 x to the 1. And write the 1 there. Nobody's going to worry about that. Next one, 1 times 4 is x to the 0. And then then what is x to the 0?
1.
Are you with me? So it'll just be 4. Happy on that? But now, oopsie, there is no x.
Dames en heren, jammer vir die onderbreking. Ons vra dat al die graad 12 leerders wat betaal het vir die opvoeding vandag, asseblief nou aan die kant gaan. Baie dankie.
So if I don't have an x and I want an x, I'm making an x. You know that I've taught you to do lots of things because I want one. I want an x there. But if I put the x there, the exponent has got to be 0. Because that still means 1. It's still the same sum as what I used to have. But then if I say 0 times the coefficient, I'm going to get 0. Okay, so it's minus 0 plus 0. What would you like? It doesn't really matter. But then the exponent will be, but this is still 0. So this is one of the rules that I'm going to teach you. When you do the derivative of a, let's say this. If f is a number, then the derivative would be 0. If there was a number 3 and the derivative would be 0. Now you're not going to do what I've just done here all the time. I'm showing you where it comes from. So if it was minus 3 and you did the derivative, you would get 0. If you want to put the x there and put the 0 there, it makes sense that 0 times anything is 0. And this is just making my life harder than it should be because it's still going to be 0. That whole answer will be 0. And for a start for now, write the 0. If you're in an exam, you're just going to leave it away because it's gone. Are you with me? I want to come back to the fact that it's gradients. So in other words, if my f was equal to 3x plus 2, tell me please what function is this? Linear, straight line. Tell me please what the gradient is.
3.
How do you know it's 3?
The equation.
There it is. But if I'm right, then this should also get to a gradient of 3. How do I get to the gradient? By doing the derivative, saying 1 times 3 is x to the 0. And then the derivative of a constant number is 0. Are you seeing what I'm seeing? So that the gradient is 0. Now tell me, if this was your straight line, please, how would I draw that? Is it a this one or a this one? Okay. Through 5. That would be y equal to 5. Are you with me? What's the gradient?
0.
0. What's the derivative? 0. You see it falling into place? Whichever one you think of, you wouldn't think that. I would ask you for the gradient and you'd say nothing. 0. But then that makes sense if I take a constant number and do the derivative that it is 0. Because you can see a straight line's gradient. And you can see when you do it this way, it does work out the same. And that it is equal to 0. Whatever the number is, y equal to, derivative of a constant is 0. Look at the graph. Straight line like this, gradient, 0. Are you with me? Showing you that all the interesting stuff. This could be in matric paper now in June, or in prelim, or in final. And this one would have been worth 3 marks. Lekker. This is usually question 1 in calculus. Do the derivative. And normally there's 2, and they differ a little bit with each other, but normally there's 2. This was as straightforward as you can go. Because it has to be separate terms, it was. There's no variable in the denominator and there was no root, so lekker. So then you get your differentiation. Now I want to write it very mathematically. How would we write this very mathematically? What we just said there. Take the exponent times the coefficient. So that would mean a times n times a, are you with me? And then still x to the power of very mathematical.
Oh, okay.
That is actually the definition. But that looks terrible when I speak speak English to you, it sounds much better. But that is the definition. And no one's going to ask you to write down the definition. It's a principle. Now we've said that the differentiation or the derivative is equal to the gradient. I want to give you all the information as a whole. Now, except for the fact that it's a gradient, it can also represent, okay, the speed of something. Alright, are you with me? Or velocity? Alright, not now. Come on. I'm putting in the picture way before. So it's different, it's strange, right? Okay, this is what we're going to be doing now all the time. I'm just putting you in the picture. So differentiation represents gradients. So that's a gradient of something. I'm not going to get into that now. You're just getting 3 marks for knowing that you should exponent times coefficient and subtract 1 from the exponent. Okay, then for further notice, the double derivative. What do you think you're going to do with double derivative? If I asked you for the first derivative, how would you get double?
Times by 2.
Do it again.
Oh.
Do it again. And if you do it again, what's going to happen? 2 times 9 is 18x to that. And this one? Minus 4. X to the 0. Derivative of a constant number is 0. So that's it. Okay, now I didn't ask you to do that. Please don't do that with all these sums. We're just doing derivative now. But if you do derivative a little bit later, it is going to represent just for future reference, to get all the stuff together here. Also, that is where you are going to find your point of inflection. Okay? Please don't think I am swearing at you now with all these words. Point of inflection, and also to do something to do with concatenity. I'm not going to explain that to you now. I just want you to have a little summary for later. Okay. For now, you are doing first derivative. That's it. Not second derivative, just first derivative. So let's get to our eventual second example. And in this example, I'm saying do the derivative, please. Now, there is notation here as well, because this was not called fx. I personally like fx, so then I'd say f dash. Derivative. That's how people speak differently as well here. I like the f dash. They say that as well. So the derivative of it is, or f dash is. Now there's not that, so you can't say y dash. That's not one of the notations. The notation here is going to be dy dx. Oh, all of these new things, but you're going to get used to it like that. It's just a notation. I'm saying y was an expression, and this is doing the derivative of y in terms of x. But it's right or it's wrong, guys. Okay. dy dx. Because y was in terms of x. So could it be y in terms of r? Then it would be dy dr. Or even p in terms of k. dp over d. Okay, are you with me? Finicky stuffies for later. Okay, but before we get there then, now I've got to do the derivative on this one. This is just for the notation, and if you don't write the correct notation, they're going to give you 1 mark minus. But also the good news is they won't give you in every single sum minus for notation, minus for notation, They penalize you once somewhere for notation. So it's not the be all and end all. But can I differentiate? No, because I cannot see the exponent and the coefficient. What must I do before I can see the coefficient and exponent? X to the 1 over 2, excellent. Exponents. In exponents, you were taught that the exponent here would be 1 over 2. For knowing that, it's a worker mark. So at least the roots are not there, it's an exponent form now. This is also a problem, man says. shouldn't be an x underneath the line in the denominator. So what can I do with it?
Times 1 over x.
Take it to the top,
Huh?
right? It shouldn't be in the denominator, so I'm taking it to the top, right? Right? Okay. Not minus a is 1 over a. Don't get confused. Exponents that are negative can become positive, whichever way, from there to there or there to there. But don't get confused and make up your own rules. Okay. So first of all, so now this is why the teaching is going on, so that I can show you all this stuff happening. So now it's separate terms. There's no more roots. There's no more variable in the denominator, and now I can start differentiating or getting the derivative or doing calculus rules. What is here? Still? Because I haven't done anything differentiating. Now when I do the differentiating, at that point it must be dy dx, not from there, not next step. The moment that I do the derivative, it must be there. Okay, are you seeing them being picky about this? And now let's get back to our rule. Take the exponent times the coefficient, giving me 1, right? 2 times a half. X to the minus a half. Because you're saying exponent times coefficient is 1. Take 1 away. It will always be 1 whole unit, 1. So that gives me minus a half. And over here, plus x negative 2. And you're done. You are done. Ma'am, can I write this better? Yes, you can. Don't. If this was the question in the exam, you're going to get a mark for writing them in the correct way and for derivative, and that's done. How can I rewrite this better? Because I would also like it to be nice. Please don't do it. Maybe I shouldn't say I like it when it's written nice. I don't. Otherwise, you're going to do it. How can this be written in a better way? Well, this one, first of all, could be with a positive exponent. Remember in grade 8 and 9, always write your answers with positive exponents. Please don't. You stop there. But is this true?
Yes.
And kids do that and we mark it correctly. But if you make a mistake there, we've got to penalize you. And now that's just silly because you could have stopped there. And the same here. This should have actually been 1 on x to the half. But x to the half should have again been. Don't do it. Perfect, but don't do it. It's 1 over x to the half, and x to the half is again back into root form. Are you with me? How could they force you to do that, but they won't? If they said to you, prove that this answer is, and then they gave you this.
Okay.
So you got to that answer, and that's how they got to their, but they won't do it. Are you with me? Please? I know we want to have positive exponents. We want to have it as nice as possible. Marks. 2 for writing in the correct way, and 2 for one of each of those. 4 marks. Lacquer, if you know your stuff.
Great.
Alright. Notation number 3. You're still going to do the same thing.
Yes.
Okay, but now look at the thing. Whether this was now fx equals or y equals, you still got to do the derivative. What's the problem with this derivative?
It's
There's an x underneath the line.
yeah.
So
It's a hill.
I'm hearing, take it to the top.
Yes. Right?
Why not?
We don't know.
That plus there, can't do it. If you do it, you've got to have brackets and take it x to the minus 1 and then still time it in, because this is division. Whole thing divided is whole thing times. Or there's other techniques. Factorize by taking out a common x. You're going to have 3x plus 1. But has that been any derivative? No calculus there. So now what's this nonsense here? It says, do the derivative of what's inside the bracket. It should still say, do the derivative of what's inside the bracket, because I haven't done anything yet. I have just rewritten it. So then the equal sign comes here. Where in those previous ones it was y equal and dy dx equal. Fx equal, f dash equal. Are you with me? This is now different. If you put the equal sign there, they're going to penalize you. That 1 middle mark for notation is going to be there. So I haven't derivatived yet. I haven't done the derivative. Are you with me?
Yes, ma'am.
Can I do it now? No, you still have to simplify. I'm still going to do it with 3x plus 1. Now whether you change your block brackets to round brackets, it really doesn't matter. So if I do the derivative now, can I now do it?
Yes.
What should be? Separate? No denominators, no roots. Are you with me? Is it derivable?
Yes.
Yes. And what is the answer?
3.
Three.
Do you see the straight line?
Yes.
Mx plus c, straight line gradient, 3, you see it?
Yes, ma'am.
Whether you thought of it or not, it's 3. Exponent times the coefficient is 3 and you subtract 1 and you get x to the 0, which is nothing. Well, it's not nothing, it's 1. And the derivative of a number is 0 because it's actually like you're having x to the 0 there, timing the exponent in, so that the answer is there. But where's the dx now? Done. I'm reading. Derivative of this thing in the bracket is 3. If you still have a big D here, not for McDonald's, if you still have a big D here, it's wrong. It's notation error. Okay. The method stays the principles, but the notation changes. And there's 4 of them. I don't know who sat and thought all 4 of these out, but anyway. So here we are, stuck on it. Then the last one of them is still looking quite the same, because isn't this still dy dx? It is. But then they can write it like dy, and you can even start here, ddx of 4x squared plus x. They can either say y and they tell you what it is, or they can give it to you just like this. So basically it looks the same as this one. It's just got a big D with a small footnote x. And this one is just d dx of. Guys, are you with me here?
Yes.
I'm not going to try and explain to you why they wanted all these notations. You've got to just know, do the derivative. Can I do the derivative?
Yes.
Yes, fantastic. There's nothing to do. There's no separating terms. There's no variables at the bottom. It's quite derivable. And the answer is?
X.
8x.
8, guys.
Exponent
Or x
times
minus
coefficient. Take away 1 is 1. Exponent 1 times coefficient 1. Take away 1 is 0. So it's actually 1x to the 0, which we don't write. What does this represent? A gradient. Please, not for now, I'm not going to do anything with it, but for later. This represents a gradient. This is why we're doing it. We're wanting to get into gradients, but I'm just showing you the technique of deriving, which is exponent times coefficient, take away 1, with all those rules. There must be separate terms, and we haven't had one like that, but in these homework sums, there will be an expression with brackets. So what are you going to do? Time out the brackets, because you have to have them separately. Okay. Whatever you do, those are your rules, guys. Some people write it very technically with lots and lots of rules, and we'll get to them, but basics is this. Just check. The most that you can use for notation is 1 mark, so you're not going to tear out your hair because of notation. Just make sure that you actually know what you're doing. But the way of doing the differentiation, that's what I'm looking at. Notation, yes, please don't throw away a mark if you can get that mark. Notation. Those sums for homework.